So this is now lecture two of the modified version of the talk on invariant maximality. So please.
Thanks. Okay, so this is lecture two of 2025. And I do want to briefly go over the status of this book, some things that happened since last week, and then I want to do an overview of this reversal. And then maybe if I have time, overview followed by some more details. Okay, so this book, the current title is Maximality. The current title is Invariant Maximality Constructions and Games. And there's a reason why I use the word construction there, and you'll see why. Okay, so it's planned to be in 6 chapters. First, the introduction, which hasn't been touched, just in my head. Um, uh, 2 has been retitled. There hasn't really been much change. 2 is the preliminary section on core mathematics, where I'm just looking at invariance in real functions. Actually, I even in section 2, I talk about also ordinals and linear orderings, but it's mainly real functions, uh, uh, piecewise linear and semi-algebraic. And I gave lectures on this early on in the early part of last year, this lecture series. Uh, the third chapter is invariant maximality derivations. This is the positive results of the subject. And that I gave a talk on a week ago, and I want to give a little bit of an update on that. And then invariant maximality reversals has been more or less constant for months. And this is what I gave one lecture on last year, but we want to restart it. And I want to do an overview today, especially an overview. Then there's this section which is retitled, which obsoletes earlier version, which is really the finite form. And I did talk about that a week ago also, and I call it finite invariant constructions. That's where the invariant construction part of the title of the book comes from. I don't call it finite invariant maximality because it isn't obviously invariant maximality as it's read. It's so indirectly reworked and interwoven that I think it's best titled as a finite invariant construction. And then the final chapter is on finite invariant games. Using game theory does allow me to simplify various things. So I have no doubt there's going to be a chapter 6 in this book, but it hasn't been written. And I don't want to get into this right now. So anyway, some more details. Invariance in RK and beyond is the preliminary core mathematical chapter, and it's upgraded from the version on my website. And what I really want to do, what I'm doing is I'm conforming the notation and terminology for the whole rest of the book. So the transition from the core mathematical stuff in chapter 2 and the red meat in chapters 3 and 4 is very smooth. That's the idea, is to make that much smoother than it has been, notationally and conceptually. Now, chapter 3, a sub about chapter 3. An upgraded version is now present on my downloadable manuscripts page. I put a manuscript up on my downloadable manuscript page, which is the current version of the introduction, of the detailed, comprehensive introduction to chapter 3, namely the positive results in this in invariant maximality. So this has got all this uh, good new stuff. It's more polished and better than what I had before. But now this is actually working even better because let me tell you the situation. Uh, Recall that there's only one notion of invariance that I'm using throughout the entire book. Only one now, and that is isomorphism. Not isomorphism, but partial isomorphism. Partial isomorphism is a one-dimensional partial map which is preserved under the when it acts coordinately on the k tuples. So that's all. That notion is enough to drive the whole subject. Now, what we have is that for some very basic, first of all, for finite functions. Oh, yeah. And invariant maximality lives entirely in Q minus 1, 1 closed, as I said last week. And for finite functions, I have a complete analysis of which functions are usable, which functions you can use. And uh, the obvious red meat is for infinite functions. Well, the natural class for infinite functions is to keep the subject order theoretic, because it's entirely order theoretic, is to use the order theoretic functions, the order theoretic f from q minus 1, 1 into q minus 1, 1. And the goal of invariant maximality is to determine which of those functions are usable. In other words, for which are the statements usable? Oh, correct. And it now appears to me that I'm well on my way to solve that problem completely. Not quite there yet, but I'm getting close to being able to, I'm getting optimistic about solving that completely, which I think is a very good situation. Let me mention a little bit more about this. If you remember, I had now as many as 9 different versions, uh, relations and roots, graphs and cliques, graphs and independent sets. All these things, they're very similar, but they're all aimed at slightly different mathematicians, slightly different combinatorics. But they're all intimately related. And then I prove they're all equivalent no matter what f I use. No matter what f I use, they're all equivalent. Well, what's very good is that your favorite version of this is going to be there because among the 9, one of them you're going to like. But the negative side is this is a whole pile of these things. Now, I do prove they're equivalent. Well, so I did, and I announced this last time, that you can consolidate them all into one statement, which then you can prove is equivalent to any one of them, namely what I call order invariant constraint. That every order invariant constraint has a realization or has an instance which is invariant, F invariant. But and I mentioned last time, there's a more general version, which is just any universal constraint. So now you can ask inside and outside, I mean, positive and negative combined. So that appears to be fine, but it now looks like I'm probably going to be able to prove that that's actually equivalent also. So that stronger thing is even equivalent. Now, there's something significant about that because The stronger one is much easier to use to refute cases of order theoretic F. Remember, we're trying to characterize all order theoretic F that are usable. If I have a tool that I can write down uh, uh, instances uh, much more easily, then I might be able to, then I should be able to accelerate the goal of figuring out exactly which order theoretic functions F are usable. So this is very exciting to me that this may well come out very well. Now, if they aren't equivalent, in other words, there's a notion of strongly usable here that's just as good as usable, except it's different, which is not the perfect situation. But if there's a notion of strongly usable, I might have a complete characterization of all order theoretic functions that are strongly usable, and that's nothing to sneeze at either. So that may be the default, but I think that maybe everything is going to come together. All right, so we're that's pretty much. Oh yeah, and I was kind of flummoxing around about whether this thing that I did with the gift at high school, I finally realized the right notation. It's OI Max emulation, one of the 9 versions, emulation uh, constantly below zero, identity below zero, and where 0 and 1 are being moved. Zero gets moved to 1. Just that. Um, I use a little more than second order arithmetic to prove that. But in the case where the set has cardinality in most 3, I was able to do that by hand for these kids. I was able to do that, and it's not clear whether this could be done for cardinality less than or equal to 4 by hand. So anyway, so I got that clarified. Now on the reversals, that hasn't changed for months. And we're going to talk about an overview. I'll try to say something sensible today about it, and how I plan to roll it out for you. Now, finite invariant constructions. This has also been put on the website, and I showed you this. This is on the explicitly pi01 forms, where I use heights in a very simple way. The height of a rational number and the height of a rational vector. And this is, I'm a lot happier about this new kind of finite form, actually, it really is. I'm a lot happier about this than any sort of routine miniaturization that you might have. This is significantly better. Okay, and again, as I haven't gotten into this, I don't want to get into this now, the games, but that's going to be important also. All right, so what are we reversing? We've been reversing the same thing forever. Talk about reversing this. And I'll write it this way. Every order invariant graph on Q minus 1, 1 to the K has a less than 0, 0, K dot, 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 K to the K invariant maximal clique. And we can review what this means because you want to make sure we're talking about the same thing. This, of course, is the space that invariant maximality lives in, and we use F invariance. Now, order invariant graphs on Q minus 1 to the K have irreflexive symmetric adjacency relation, which is order invariant as a subset of double the dimension, right? And this, now I don't talk about this invariance. I used to think of this as an adjective and not a noun. Now it's both an adjective and a noun. It's technically a noun and therefore an adjective in this context. This is a function, right? its domain is this, and it's the identity on the interval, and it sends each I over k to I plus 1 over k. Okay, so that's what we're reversing. And that's equivalent to a large number of variants, right? I just uh, I just got attracted to doing this with the cliques, and I think it's convenient and all that. Now, this is chapter 4 that does the reversal. And here's what chapter 4 looks like, the sections in chapter 4. Uh, and we're going to talk about the structure of this proof, of this reversal. Really, the line of demarcation in this is right here. That's a section that's put in because naturally you would think that I would define this horrible graph that's order invariant, that I'm getting this large cardinals out of. But you can't do that because it's too complicated. Does anybody want to read 25 pages of a definition of a graph? They have no idea what the clauses, why the clauses are fitting together this way. I mean, so can't do that. So what I do is I actually assume the definition has been made and quote uh, pieces of the definition as I need them. But then I have to actually make sure that I didn't cheat. So we have this non-cheating section here that actually does get everything written down somehow right here. That's important. And I may be talking about a fictional graph for all you know. All right. And then after this, I move fast to get away from uh, get away. I no longer work with the graph and the arbitrary maximal clique in the graph. In here, I work entirely with the graph and an arbitrary maximal clique and develop a whole theory. But then I take what I need, forget about the graph and the maximal clique, and build a structure independently of that. I mean, based on that, I build a structure extracting what I care about, and then I go from there to the rest. So it's really kind of two sections with this 4.6 honesty section, 4.6 honesty section uh, designed to make sure that I didn't cheat. All right. And by the way, it turns out that the reversal can be done in RCA naught. The reversal is not done in RCA naught, it's done in WKL naught. But then there's a bunch of stuff that I have to do, that I can do of a general nature that tells me that automatically the proof can be converted to a proof in RCA naught. So that this is an interesting thing. But that's that's at the end. So the way I do this, I start by fixing a number, and I really want it to be big, so I didn't care about how big. 1,000, the 3 means 2 to the 2 to the 2 to the 1,000. I think I've got it. I have to check whether I did this way. I think it means 3 2s followed by 1,000 on top. Okay, that's a pretty big number. And we look at it, and now K12 is 12 twos followed by K on top. So that's a ridiculously big number. But anyways, one of the big open questions in this whole thing, of course, is actually doing reversals where I am sensitive to the dimension. Obviously, I'm not sensitive to the dimension here at all. And but when I give the proofs on the positive part, I've always been, even last year, I've always been careful to use the minimum amount that seemed to be uh, needed, seemed to be needed, with an obvious reversal being conjectured. But the actual reversals are very insensitive that I have. Yeah. So, and we let S be any maximal clique, which is also invariant. I shouldn't say, I don't know why this is wrong. Just invariant. Yeah. Okay. So now there are three substantial obstacles. There are three substantial obstacles needed to be overcome in this reversal. One is that the statement being reversed doesn't have obvious ingredients for developing any kind of comprehension or separation. See, Borel diagonalization, and going back in my career many years ago when I used to do Borel functions, we've come down from Borel functions to explicitly pi 0, 1, by the way, which shows you how old I must be since I managed to do that. In Borel, or even Borel determinacy, and that which is even earlier than Borel diagonalization, I'm asking that you get, well, but no, Borel determinacy is even clearer. There you have a Borel, you have an object that's a strategy. And a strategy packs a lot of power. And so you have something to work with. You can get a Mago models out of that. And Borel diagonalization says you can't Borel diagonalize. Well, the counterexample is going to be some real or some infinite sequence of reals, you see. And that's an object you can get your hands on that you might be able to build something out of. So that's how those reversals work. Well, here, the only thing you have to work with is that has any possible information is going to be, it's not the graph. I mean, that's given. It's got to be the maximal clique, right? So you've got to be able to get information out of the maximal clique. All right. So the maximal clique. Now, there's a hint of relevant information in a maximal clique. Namely, membership in a maximal clique is equivalent to a universally quantified atomic statement, namely that you can put it in without keeping it a clique. If you can put it in keeping it a clique, then it has to be already in. So being compatible with everything in me, that's equivalent to being in me. So that's a kind of atomic equivalent of a universal statement. Doesn't sound like that's a lot to work with, but that's all you got to work with. Another obstacle is that although the statement being reversed has a hint of indiscernibles, and we kind of know, okay, I don't know when is the exact time history of this, but you kind of know that you want to get separate. Well, no, we know from general set theory and various standard things and so forth that separation alone may not be that strong, but separation combined with some indiscernibility give you large cardinals if you're in the right context and you're lucky. So we definitely want indiscernibles. So the statement being reversed has a hint of indiscernibles already, but it's very rudimentary. It's an atomic indiscernibility with only k plus 1 indiscernibles. The atomic indiscernibility embedded in the statement is 0 is the fraction 0 over k to k over k. And we use parameters less than 0, right? So that indiscernibility is rather weak. It's far from, well, first of all, there's only k plus one of them, but that's not so serious. But the point is that and then the parameters are only less than the smallest one. That may be a little annoying, right? But also the main point is it's only for atomics. In other words, you're not getting indiscernibility with respect to arbitrarily quantified formulas, which is normally what you want. Now, there's another obstacle, and that's the domain is a dense linear ordering. I mean, the domain is Q minus 1, 1 closed. That's horribly ill-founded, even internally. Right? I mean, it doesn't support internal or external inductive constructions. In order to get reversals anywhere, you got to be building up ordinals, doing transfinite recursions in order to get anywhere, right? So we don't have that either. So we gradually have to overcome these obstacles, leveraging advances in any one of these three with advances in the other two. Yeah, so that's kind of cute. You make some progress in one of them, and all of a sudden you can use that to make some progresses in another one, and then so forth. They sort of go back and forth into so you get at the end you get everything in pretty good shape. After you overcome these obstacles, you can hope to do a fairly standard kind of math logic construction, because now you'll have transfinite recursions internally at least, and you'll have indiscernibles, and you'll have separation, comprehension or separation, and then you're in unfamiliar ground. And that's exactly what happens at the very end of this reversal. A principal tool here, by the way, because you're starting off so impoverished, is to use finite languages. We most commonly use the finite language L, K1, K1, K. K1 is 2 to the K. Ah, yes, we have 1, 2, followed by K on top. There's only 1, 2. 2 to the K is K of 1. Okay, and this is based on the signature R less than, where R is K array, and with K, we only have K of 1 variables, and we have formulas of complexity at most K of 1, with quantifiers allowed, right? Quantifier, we have complexity. Yeah, complexity is going to be measured every time you do something. In other words, you uh, uh, quantify, that adds 1, or if you negate, that adds 1, or if you disjunct, that adds 1. Just sort of normal, no fancy complexity. All right, now we call our fixed k greater or equal to 1003. We only arrive at the normal first order language L of k. So there's a normal first order language L of k, which has the same signature that we're talking about, but with arbitrary applications of connectors and quantifiers, and therefore an infinite set of normal indiscernibles. We only get that comforting situation in section 410, which is quite late. The comprehension, which we call representation at early stages, and later we call it separation, is also only for this finite language that I mentioned. Only finding many formulas in this language until the end of section 4.7. You may want to look at what these section numbers are like again. See, this is after the no cheat section. uh, into here. Way 410 is where I really get my indiscernibles in perfect shape. I get my separation is pretty much in perfect shape here at the end of here, the end of there. And then the internal well-foundedness, well-orderedness comes in here. Internal well-orderedness comes in here. Full separation comes in here. And the indiscernibles being full and infinite in size come in here. Okay. And all of this is horrible stuff uh, living in Q minus 1, with the graph and the maximal clique being the objects, the only structure. Okay. All right. Yeah. So as I said, these finite languages, representation at early stages, later separation only for this finite language until the end of section 4.7. We obtained a suitable structure which is internally well ordered in section 4.9 in convenient second order form with a full form of separation, but only with its weaker indiscernibles, and the indiscernibles are upgraded to normal in section 4.10, one more section, releasing our constant finally. We release our constant. See, that last step is done by a compactness argument reflecting on the fact that K was arbitrary. That's why we removed K. See, various pieces help other pieces. We then build on these achievements in more or less standard ways later, section 4.10 and section 4.11. That's when we have everything in good order. Now, the graph G is far too complicated to abuse the reader with a definition of it all at once. You wouldn't know why the various pieces were made. They're rather technical and blah, blah, blah. All right. So in sections 4.3 through 4.5, we pretend we've already defined the graph and cite the properties of the graph and its arbitrary maximal clique, arbitrary invariant maximal clique along the way. We then inventory all these cited properties and turn that into a honest definition of G. In section 4.6, that's the honesty section, keeping ourselves honest. I've never been so honest, I promise. All right, GS is only used in sections 4.3 to 4.5, as I said, and GS lives in this space of dimension K12, which is 12 twos with a K on top. And in sections 4.7, 4.8, we move to Q0 infinity with these limited indiscernibles. The indiscernibles we expect only this language with finally many formulas. In preparation for this convenient move, we have a considerable development in 4.3 to 4.5. There's plenty of development in here. In atomic representation, which is the first real section that we get going, section 4.3, we obtained a weak form of comprehension in which relations defined in actually it's right here. I should have said a second. Relations defined in this language are represented atomically with parameters. Now, look, in set theory, you say that any subset of any set can be represented atomically with a parameter, namely the parameter is the set, right? In other words, uh, if you have a formula carving out, say, natural numbers, you can write it as n in x, where x is a parameter, namely x is the set. This is atomic representation for this language, but it's only an atomic. It's an atomic representation. Yeah, yeah. So it's very strong, but for a limited language. I'm sorry. I want to make a main point here. This is we get that this is see in set theory, the number of parameters needed to represent something atomically is one parameter. But we have no control over the number of parameters being used in the representation. I would say no control, no decent control. Now you'll see how dramatically this changes. All right. Now looking at our function that we're doing invariance with respect to, right? We can think of zero as a critical point. So we don't now pretend we're set this. We can think of zero as a critical point and an indiscernible 0k to k over k. We can't do much with the numbers, the non-negative numbers, but we can do much more with the negative numbers using that they're below the critical point being zero. In this chapter called, in this section called negative reduction, 4.4, we obtain negative rationals R1 through R2 dot 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 infinite sequence strictly increasing with sub zero, which form new indiscernibles with R1 acting as a new critical point. We still have the indiscernibility uh, with respect to only a finite, with respect to only L of K1, K1, K. Right? Thus, we're working with, what we're really doing is we're working with G comma S, G being the graph and S being the maximal clique, the invariant maximal clique, restricted to Q minus 1, 0, restricted to the negative numbers. We also maintain the atomic representation of relations defined in, yeah. I'd written this before where I thought it was, I, I didn't realize how useful it is just to be specific about the language. While still working here in section 4.5, we develop, this is the section on tupling. This is a section on tupling. It's called tupling. We develop length less than k tupling, which is needed to strengthen the atomic representation for this language. This has the drawback that the number, now here's a crucial point. This has the drawback that the number of parameters used in the atomic representations is not controlled. In section 4.5, we established that only 5 parameters is enough. I mean, we know that some number of parameters is enough, like the number of parameters in the thing you're trying to do an atomic representation of, but that's not fair. You want only a few. And that's very important. Uh, this is what happens in set theory, why it has such power. You have a whole pile of things, and it all becomes one object. That's atomic representation with one parameter. All right, this is our representation slash one. This is a name I gave, which undergoes many upgrades in section 4.7. 4.7 is after the no cheating section, right? In section 4.7, arriving there with a full separation, with what amounts to full separation. I'll write that. There's nothing, okay. Yeah. Well, section 4.7 starts with a convenient transfer of this situation, this negative situation, isomorphically to another structure, M equals Q0 infinity less than R 1, 2, dot, dot, dot. It's actually that transfer is made at the end of section 4.5, where R is K area and the numbers 1, 2, dot, dot, dot are indiscernibles. Again, we're stuck with limited indiscernibles. The language is limited. We also have R representation slash one from section 4.5. So we have some sort of, we're getting off the ground something about comprehension. In section 4.7, the representation one gets upgraded several times, including resulting in full LK separation, where arbitrary definable relations are represented by a relation of fixed complexity with 7 parameters. Okay. In set theory, the complexity is atomic and there's one parameter. Here, the complexity is some fixed complexity, some when I say fixed, I mean much smaller than K with 7 parameters. This is important. This allows you to uh, build strength. Strength needs, well, in addition to having some indiscernibility generally, you want comprehension to be in a form like this. We now have the separation in good shape, but the indiscernibility is still only for this limited language, and the domain is still dense. This domain is really a nuisance. It's just horrible. In section 4.8, we define a pre-well ordering of M, which leverages the normal separation plus enough indiscernibility. In other words, to actually define this pre-well ordering, which we need to have, it's isomorphism, equivalence classes under internal isomorphism, and blah, 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 all that stuff. You need to have some separation, and you need to have real separation plus some indiscernibility. It turns out you don't need a lot, which is fortunate. See, I got lucky with all this. And so then we get the internally well-ordered structure X, which is D less than pair set. Okay, so now we arrive at at the crucially important second order structure. Second order, I don't mean that something is uncountable here or anything. I just mean that's the way it's organized. We have a domain D, a literally ordered domain D, and a pairing function on it with a family of things called sets, the internal sets, membership, and then a stratification of set. Also, the C's are language restricted indiscernible elements of D. Yeah. In other words, they're not full indiscernibles yet. We still haven't done that. The constant K still appears at this point, not directly in the formation of the structure, but indirectly in terms of this level of indiscernibility of the seas. So the only remnant of holding back here is I mean, we've got a really good situation here. We have internal well ordering. We have full separation or relevantly full separation, but we're holding back a little bit in the indiscernibles. This is only with respect to a finite language. But now we can fix that because what we do is reflect on everything we've done so far. Note that k is an arbitrary integer of sufficient size to support a compactness argument that removes k from the development. We then have the structure X with an appropriate full separation, full indiscernibles, and internal well ordering. We then build the internal constructible hierarchy in section 410 by standard techniques. In other words, people have been doing Gödel's monograph, in various contexts, uh, forever, right? I mean, this is now standard kind of stuff, even though it's messy, the details. Now, in section 411, we then go on to derive con SRP using the indiscernibles to verify the relevant large cardinal properties internally. The relevant large cardinal properties have to be a little bit careful. You want to use the subtle cardinal hierarchy, which is known to be cofinal in the SRP hierarchy. So you get con SRP this way. Excuse me. This ends the overview of the reversal. All right, now I'll go on for somewhat longer with some more details, but this is the way I want to organize this lecture series on the reversal. First of all, I'm going to publish this lecture notes here on my downloadable lecture notes site, citing the lecture. I've already done that kind of thing for the previous lectures last year. So you'll get to read this overview anytime you want. That's number one. Number two, I'm going to roll out the exact chapter 4 in all its glory as I give these lectures on the reversal. So consider this a lecture on the reversal up to 4.5. So you're going to see I will put on downloadable manuscripts page, and I already have something there. It probably has to be changed a little bit, not much. A downloadable manuscripts page, already a big initial segment, a serious initial segment of the reversal manuscript. And so you can hear this sanitized, simplified version of the actual manuscript, which is impossible to go through in detail and have anybody understand it in a lecture. But you'll see that, and you'll be able to refer to the actual manuscript almost immediately after, as I roll out the actual reversal manuscript. My idea being that every time I give a lecture on this, I will be checking the details finally so that I'm happy to release. Okay, so by tonight, sometimes there's already a version of an initial part of the reversal manuscript, already something on the downloadable manuscript page, but probably it'll be superseded by a little bit better one by tonight. So I think that's the way that this can actually work. And the overview, namely this particular lecture, will be on the downloadable lecture notes page where I list the lectures. So you have the overview, plus you got me lecturing on roughly how these various parts of the uh, manuscript work, plus the actual manuscripts checked on the downloadable manuscript page. All right. Andreas, can I have some more time?
It's
All
up
right.
to you. Yeah.
I'll take some more time. So there's this section called atomic representation. And as I said in the overview, this is based on finite languages. Now, it turns out that this is the main, from the overview, you can tell that this is the main language that's seriously used throughout the reversal. But there's some, and that involves only a k-ary relation. But there's another language that only involves a k4 relation. That's four twos followed by a k, 2 to the 2 to the 2 to the 2 to the k. That's the arity. Okay. And then there's another one that has this arity. And, and these tell you how many variables and what the complexity is, variables and complexity. The zero means quantifier free. For technical reasons, these get temporarily used. But this is the headline one. Now, when you see the actual manuscript, you see everything, right? All right. Now it starts to get a little technical. There's only certain assignments I want to use for these languages. So never mind, just get the idea. All right. So there's three atomic representation theorems. They say that every relation defined in a certain language is atomically represented. So the first one is the most important one. And here the quantifiers range over Q, over a number picked below zero, a negative number picked below zero. That means the quantifiers range over that. So this formula, and it's the ith formula it's the ith formula in an ad hoc enumeration, almost ad hoc. Not, I mean, you'll want to be a little more careful than that of the formulas. Uh, So this is going to be equivalent to, I always have a dual form. One is in negated form and the other is in a positive form. And the parameters are these numbers here. And these are among the indiscernibles, by the way. All right. You see, so in the X stays here. You get the idea. Now, this is a pretty bad atomic representation. This is pretty bad because I keep telling you before when I was talking about the overview, the number of parameters used in the number of parameters used in the atomic representation is bad. In other words, I'm using as many as k over 12. I mean, 2i. Actually, how big is I? Well, there's this number, which is a very big number. It's not as big as k of 12. There's this number associated with the language that we're talking about, uh, the language that this is enumerating formulas on. So it's a lot. It's an atomic representation, but the number of parameters is gigantic, and this is not too good. So as I said in the overview, we work on trying to cut this down. Actually, we cut it down to 5 parameters, ultimately to 7 parameters in a slightly different, more advanced context. But the whole point is the complexity is small, which is because it's atomic or negated. And this is done by induction on the complexity of the formulas. You have to show that every time you put a quantifier on, you can handle this. But remember, we only have one tool, a maximal clique. You've got to show that the maximal clique gives you quantifier, it has a quantifier elimination, is a kind of is a tool, is fuel for a quantifier elimination argument. So all of this is in the real manuscript. All right. Then we also do this for the other languages. It's slightly more technical. But we in the other languages, we only care about quantifier free formulas. All right. This gets used in some way that I can't describe to you right now in a later chapter. But the main one is the first one. So you understand you have atomic, yeah, this is also atomic representation or negated atomic representation, also. And that's important because there are connectives in this. Even though this is quantifier free, there are connectives going on here, connectives in this language. Then the next chapter or section in this reversal is called negative reduction. Here, what I want to do is I want to take everything that's going on, all my indiscernibles, which are non-negative, these fractions that are non-negative. I want to push everything interesting down into the negative numbers because I can do a lot more there because I know that they're below the critical point. The critical point, so to speak, quote unquote, critical point in this setup is zero. Remember, that's why I have -1, 1 is the interval I'm working on. Zero is this critical point, and these other numbers are indiscernibles, 1 over k, 2 over k, 3 over k. Except it's not k, it's k12 because I want to make the dimension big. Uh, so if I can push everything down the negatives, I can do better. Now, I didn't say in the overview the real mileage I get by going down into the negatives. The real mileage I get is if you remember, the statement I'm reversing just has indiscernibles, and the parameters with the indiscernibles are below the first indiscernible only. Now you know that the really strong indiscernibles are more powerful than that. If you take any parameters below the ith indiscernible, then you can move the ith indiscernible and higher around, right? In other words, not just below not just below the first indiscernible, but below any indiscernible, you can move the others around. I mean, if you remember, I think maybe this is first discussed seriously in Paris-Harrington theory. That's where that is. Okay. So um, that's what I'm going to get, and I have no chance of getting that if I don't get myself thrown into the negative numbers. That's why I want to throw myself into the negative numbers in order to be able to pull something like that off. So ultimately, I get uh, these after a difficult development. This is not, after a difficult development, too much to talk about in a lecture easily. I get this infinite sequence converging to zero, such that these are now my replacements for 0 over k, 1 over k, 2 over k through k over k. Actually, when I say k, I meant k12. Exponential. And these are going to be. I'm going to preserve my atomic representation stuff. I'm going to preserve my atomic representation stuff using parameters as I did before, which are the indiscernibles. Okay. And then on the indiscernible side of things, I get this, it's horrible to write down. I get this stuff about any finite number of indiscernibles of the same order type look the same with respect to parameters that are below all of them. just like I said, when you do Paris-Harrington theory. So this is Paris-Harrington theory indiscernibles, if you like. I mean, those indiscernibles may have been preceded. I don't know what the history. Those that's where the first place they occur in the integers. Except, I'm sorry, Paris-Harrington indiscernibles aren't that strong. There has to be a gap. You can't use the ones lower than a given indiscernible. You have to use the parameters below the indiscernible that precedes the least. Yeah, so that's not right. Paris, it's the one in set theory with subtle cardinals that I'm talking about that precede Paris-Harrington. Yeah, Paris-Harrington has to be weaker. All right, so this is the obvious indiscernibility that you want. Just technically written down. All right. Now, that's all of the negative side. And look, I've gained something. I mean, I still have this crappy atomic representability with massive numbers of constants. But but uh but now I have better indiscernibility than I had before. And I have infinitely many indiscernibles. I have better indiscernibility because it isn't just below the first indiscernible. Now we want to make sure that I want to be able to have only five. I'd love to have just one, but I want a decent number of parameters. I'm tired of having the number of parameters be related to the number of parameters when I that I'm trying to analyze, right? So that's really tupling, right? Isn't that just a matter of tupling, right? Tupling. So that's section 5 is called tupling. And I have to figure out how I can do tupling decently. So it turns out that's a long story too. That's not easy. That goes on for quite a while. And and finally I arrive at what I'm looking for, which is only need 5 parameters, sorry, P1 through P5, when I want to represent something atomically. Again, I'm still only doing formulas in this language. So I'm still, this is not a full language. It's a finite language, and but at least I'm doing only five constants. This is a huge help. And then I can restate the indiscernibility that I have, which is again this is language dependent, as I said, but it's indiscernibility of the right kind. In other words, when things are the same order type, you can look below with parameters below, as long as the formula isn't too bad in here. So that's what we get after tupling. And then I actually instead of looking at the negative numbers going up to 0, I just trivially make an order isomorphism. So it's now 0 to infinity instead of -1 to 0, right? It's 0 to infinity. And I just transcribe everything I said. Oh, and the tupling is actually now made coherent. I mean, I was telling you before I was using the tupling to get 5 parameters. Now it's important to actually say what the tupling is like, because I'm going to actually use it to leverage off of and get even more goodies. So it's just an atomic kind of tupling for K-1 tuples, R of Px. And if you have the same max and the same P, then X equals Y. Yeah, this is a technical restriction. It's not quite as strong as you'd like, but it's all you can get. This is a subtle matter. I don't want to necessarily go into it today so much. And if the max of X is less than N, then this P is less than N. And remember, this is only for K-1 tuples. And this is good enough for me to get down to 5 parameters, because the number of the number of free variables I'm going to be thrown at is only from the language I'm working, the language I'm analyzing, which is L of K1, K1, K. You see. So, all right. So, all right. So, our representation one, let phi be a formula of this language, and there exists five. Yeah, this is what I was saying. Yeah. Okay. And this is the inner. Okay. So I know this is a little bit complicated, but I think you basically have the idea that I have in mind. The actual this will always be followed by the actual manuscript from which this is derived in all of its glory detail. Uh, Tonight, probably, unless I find something I have to change, might take me longer, but I think we should be all right. All right, so this is I think more than enough for today. So we can stop recording.